Okay, so now that we're done looking at linear functions and quadratic functions, we're going to start looking at different types of functions. Specifically, we'll start looking at power functions and then polynomial functions, rational functions, exponential functions, and then we'll finish off with logarithmic functions. So for power functions, a power function is basically a function of the form f of x equals k times x to the p, where k is just a constant, is just a number, and p is also any real number. So you saw that a linear function was y equals mx plus b, and then a quadratic function, or I can say f of x equals that, f of x equals y equals ax squared plus bx plus c. So now a power function is a function that looks like this, k times x to the p. Okay, so x is the base and p is a power. So we will focus more on functions, power functions with integer exponents, where p is just an integer. It's not like a fraction or a decimal. So let's look at the next functions and see if they are power functions. So 9x to the second power, is that a power function? Yes, it is a power function with k equals 9 and p equals 2, right? K is 9 and p is 2. What about this one? Second one, 9x squared plus 10. This is not a power function because of this plus 10. So power function is only one term, k times x to the p. The third one, f of x equals 6 times 6 to the x. No, this is not a power function because it's not of the form k times x to the p. You notice that x, the variable, has to be the base, not the exponent. All right, the next one, 10 times x to the 1/3. K times x to the p. Yes, it looks like k is 10 and then p is 1/3. Okay, next one, f of x equals 2/5 x to the -4. K times x to the p. Yes, it is a power function with k equals 2/5 and then p equals -4. Okay, so you notice that for these, we had, for the ones that are power functions, p was 2, p was 1/3, p was -4. So p basically can be anything, but we are going to look at when p is an integer, positive or negative. So like example 1 and example 5. Okay, so now that we know how these power functions look like, k times x to the p, our next goal is going to be to look at how the graphs of power functions look like, and then how to use these power functions to solve some applied problems. So the graphs and solving applied problems. Like I said, we're going to stick with power functions with p being an integer. So the graphs for power functions are a little different. So for linear functions, the graph was a line, and then for quadratic, it was a parabola. We'll see that power functions have different graphs depending on the parity and sign of p. What do I mean by that? The parity means if p is even or odd, and the sign means if it's positive or negative. So we'll see what we mean by that on the next page. So let's look at the graphs for some specific power functions. So we're interested in a power function with p positive and even and k positive. So can you think of an example, f of x, where k is positive, I don't know, let's put 2, times x, p has to be positive and even. So a positive and even number, let's say 4. So this is an example of a power function that satisfies these three values. So let's look at the graph. Okay, so we can do the graph using our calculator. So we go to y equals, and we're going to put exactly the power function we just wrote. 2 times x to the power 4. So let's pick a good window. It looks like -8 to 8, Negative 8 to 8, it's a square one, so we can leave that and see how the graph looks like. So when you hit graph, you see that our function basically looks like a parabola, right? So if I wanted to graph it, let's put the graph right here. So the graph is basically a parabola, more flat at the origin. So this fourth is basically just means that it's flatter at the origin than a regular parabola, like 2x squared. This is your x and this is your y. Alright, so this is how it looks like. So let's answer some of the questions. What is the domain of this power function? So the domain, remember, it's all the x values. So you notice that x can be anything. If x is negative 3, for example, I have a y value. If x is negative 10, I have a y value. So any x is going to work. So the domain is negative infinity to infinity. The range, you notice that I have y values. I have graph above the x-axis and including at 0. So the range is 0 to infinity. Now, what is the end behavior of this power function? What do we mean by end behavior? It means how does the function behave when x is really large, so when x is here close to infinity, or when x is really small, when it's close to negative infinity. So you notice that as x goes to infinity, this graph would be up here somewhere, up to infinity. So as x goes to infinity, the graphs, the y values also go to infinity. So how do we write this? We say that as x arrow infinity, as x goes to infinity, as x goes really, really large, the y value also goes to infinity. Now, as x goes to negative infinity, really, really small value, you'll see that the graph also would be up here somewhere off the charts, right? So then we say that as x goes to negative infinity, the graph also goes to infinity. It goes up. Let's change from k positive to k negative and see what's the only difference. So if we go to y, instead of 2, let me put negative 2. So I'm going to insert and put the negative and then graph. The only thing that changed is basically that it flipped over the x-axis. So when k is negative, it flips over the x-axis. Alright, so let's do another example. We're going to graph a power function that has p negative and even and k negative. Okay, so a power function is of the form y equals k times x to the p. So y is going to be, k has to be negative. So let's put a negative number. I know, negative 3. And then x to the p has to be negative and even. So it looks like negative 6 will work. Okay? Let's graph it and see how it looks like. So you go to your calculator. Let's clear that out and then put negative 3x to the power negative 6 and hit graph. So this is how the graph is going to look now. You see how it's totally different than before. So these power functions have different types of graphs. So let's graph that quick. So in here, I'm going to graph it. This is my x, this is my y. The graph basically looks like this. Okay, so what is the domain of this power function? Well, you see that I have, when x is 2, for example, I have y value. When x is 3, I have y value. And x is really large, I have a y value. The only time I don't have a y value is when x is 0. Right? When it's negative 2, I have a y value. When it's negative 3, I have a y value. When it's negative 1,000,000, I have a y value. But the only time I don't have a y value is when x is 0. So the domain is everything but 0. So you can write this as negative infinity to 0, parentheses, not including 0, union 0 to infinity. And this is because you guys saw in the review for rules of exponents, I can write x to the negative 6, 1 over x to the 6. So I can't divide by 0, so 0 cannot be in the domain. So that's why the domain is everything but 0. For the range, you see that the graph is below the x-axis and not on the x-axis. So the range is going to be 0. Actually, it's not 0. It's negative infinity to 0, right? It's below the x-axis. What is the end behavior of this power function? So as x goes to infinity, it looks like the graph approaches. So as x is 2, the y value is this. As x is 3, the y value is this. As x is 10, the y value is this. You see how the y values get closer and closer to 0? So as x goes to infinity, the y value goes to 0. The y, the graph, approaches 0. And then as x goes to negative infinity, again, the graph approaches 0. So to find the graphs of the other power functions, you basically play around with all the other options. You're going to let p be positive and odd, or positive and even, and all that, and then you'll see how the graph looks like. So you do not have to memorize how these shapes look like. Just use your calculator and graph the power function there that you are asked to graph. And for example, if you are given a power function, if you are given a graph and asked to say what is the value of k, and for example, if you are given this and you're asked what is k, is it positive or negative, and p, is it positive or negative or even or odd. Basically, you can play around with these values and see for which values the graph looks like that. So if you go in here, let's play around and say y is, let's make, well, you know that k just flips it over the x-axis, so this is not going to work. So let's change the value to the exponent to, like, I don't know, 3. Oh, it does look like this. So basically you go back in here, so you have your answer. K is negative and p is negative and odd. K is negative and p is negative and odd. If you would have picked something else, I don't know, let's pick 5, for example, and graph it. Oops. You see how it doesn't look like that? So you just have to play around with those values until you get the graph that you need. Okay, so now let's look at some applications of power functions. So consider the power function y equals k to the x. So basically p is 1 in this case, and this is just a linear function. So this means that all linear functions are all linear functions, not all linear functions. All linear functions with y-intercept 0 are power functions. So if we are in this case, we basically say that y varies directly with the quantity x. So if we have y equals k times x, we say that y, the variable, the output, varies directly with the input x, and k is called the constant of variation or constant of proportionality. So let's look at an example. For a particular college, the cost of tuition varies directly as the number of credit hours a student takes. So as soon as you see that you have varies directly, you're basically going to write that y equals k times x. It means you are in this case. But in your case, what is y? What varies directly with what? Well, tuition varies directly with credit hours. So you can write this just to make sense to you, y is tuition and equals k times credit, if you want. Or you can keep in mind that y is tuition and x is credit. So now if the total cost of 9 credit hours, so when C is 9, the tuition is 830. Basically you plugged in C is 9 and tuition is 830, and K, you don't know what K is. So basically you're going to solve for K. So K is going to be 830 divided by 9. So 830 divided by 9. We get that K is 92.22. Okay? So now you can answer the question. How much does it cost for 12 hours? So then you copy your formula again with the right T now. So T equals K times C, but you just found that K is 92.22 times C. So the cost of tuition for 12 hours is going to be 92.22 times 12. So the tuition, it will be times 12. So 1106. Okay, so this is how much it will cost to take 12 hours at this community college or whatever. Now, let's look at another example. The volume of a sphere, V, varies directly with the cube of its radius, R. And they tell you that the constant of proportionality is K equals 4 pi over 3. So varies directly. So Y varies directly with the radius, but it says it's cubed. So basically, to write down the formula, we know that V equals K times the radius cubed, because it varies directly with the cube, not just with the radius. And they say that K is 4 pi over 3. So basically V, instead of K, I put 4 pi over 3 and then R cubed. This is actually the formula for the volume of a sphere. Now, what happens to the volume if the radius doubles? One might think intuitively, oh, if I double the radius, the volume is going to double. But that's not what it takes. That's not what takes place. If the radius doubles, so instead of R, I would have 2R. So radius doubles means I would have 2R. So now the formula would be V equals 4 pi over 3 2R everything cubed. So now you distribute the exponent, you review the rules of exponents, and you know that you distribute the exponent. So that's going to be 2 cubed times R cubed. So if you look at this beginning one, this beginning one and this one, you notice that the only difference is that this 2 to the third, which is 8. So that means that the volume gets multiplied by a factor of 8. So it doesn't just double, it gets multiplied by a factor of 8. So the volume gets multiplied by 8. All right, what happens to the volume if the radius triples? So now the volume will be 4 pi over 3. Instead of the radius, I have 3 the radius to the third power. So then the volume becomes 4 pi over 3, the radius cubed, and then 3 cubed, which is 27. So the volume gets multiplied by a factor of 27 when the radius triples. So the volume doesn't just triple. What happens to the volume if the radius is halved? Well, basically now we're going to have 4 pi over 3. Instead of the radius, we'll have radius over 2 because it halved. So V equals 4 pi over 3 radius cubed over 2 cubed. So the volume is 4/3 times r cubed. And then this is like 1/8. So you could either say that the volume gets multiplied by 1/8 or gets divided by 8. So the volume gets multiplied or divided by 8, depending on how the question is asked. Okay, so these are examples of power functions and how they're used in word problems. You'll practice more in the homework. So just keep in mind how a power function looks like, what's the form of a power function, how to get the graphs, and how to play around with k being positive or negative, p being negative or positive or even or odd, and then how to deal with direct variation and questions like this. What happens to the output if the input gets doubled or tripled or halved, stuff like that.